Hey, this is Leach with Simpson Math, and today we will be completing our discussion about graphing rational functions. Last time we looked at how to find our horizontal and vertical asymptotes and holes, and we plotted our x, y-intercepts, holes, and our vertical and horizontal asymptotes on a graph, and we just made those notes. In this video, we're going to be completing the graphs by simply just adding some more points. So let's just review our topics from last time. So first up, whenever you see a rational function, we know it's a rational function because you have a polynomial divided by another polynomial. First, we identify what's our horizontal asymptote. There's going to be some version of a horizontal asymptote. So you look at the degree of the numerator and the degree of the denominator. Note whether it's top-heavy, has equal powers, or bottom-heavy. We'll be looking at rational functions that have equal powers and bottom-heavy. If it has equal powers, remember, you just take a look at the leading coefficients, and it's just simply a ratio of the leading coefficients, a over b. If it's bottom-heavy, if the degree of the denominator is bigger than the degree of the numerator, then it's just simply y equals 0 every time. Then recall we write our domain. So you need to find your domain by factoring the denominator. You set the denominator to be not equal to 0 and then solve. And those restrictions, those x values you find, those are the values that x cannot be. And so you exclude those from the domain. Then, to find our vertical asymptotes and holes, we should have already factored the denominator, so go ahead and factor the numerator. The factors that reduce, they lead to the hole's x value. All right, the ones that do not reduce, those are your vertical asymptotes. Now to find the hole's y value, you plug in that x value into the reduced function to get the hole's y value. Then to find our x-intercept, you just simply set the numerator equal to 0 and then solve. And then to find the y-intercept, you set the function to find the y-intercept, you evaluate the function at 0, so plug 0 into all the x's, and then that is your y-intercept. Make sure to write x and y-intercepts as ordered pairs. All right, for today's video, the new part for today is we are going to be evaluating the function at multiple strategic x values. So I want at least 3 points between our vertical asymptotes and 2 points from a vertical asymptote to infinity or negative infinity. So just say I have a horizontal asymptote here, and I have 3 vertical asymptotes here. So between these 2 vertical asymptotes, I want at least 3 points. Between these 2 vertical asymptotes, I want at least 3 points found. And then from this vertical asymptote to infinity, pick 2. From the vertical asymptote to infinity, pick 2. It'd be good to probably pick one that's closer to a vertical asymptote and then one that is further along. But sometimes you might need to pick more than 2 or the 3 points, as you'll see in today's examples. Basically, you want to pick enough points that you understand what's happening with the graph. You don't miss any weird literal twists or turns in the graph. So let's look at our first example. So now these are the examples that we saw in the last video. So we're just picking up where we left off in those, and we're just going to simply be adding more dots. So all this is the same from last time. If you need a refresher on where I got all those values, take a look at that video. All right, so now I knew I knew about these dots here because this is just after the x plus 2 is reduced to 1. I'm left with just 1 over x minus 2. So that's just my rational parent function of 1 over x shifted right to 2. So I could just simply graph these points. It's my half 2, 1, 1, 2, half, when I'm counting from my now moved sort of kind of origin or intersection of asymptotes. And then the same thing on the other side, negative half, negative 2, negative 1, and negative 2, negative half. So that's how I got those points. But if you didn't understand that it was from transformations, we can just simply plug in some x values. So here I've plugged in 0 into my function, and I get 1 over 0 minus 2, which just simplifies to be a negative half. And I do the same for all 6 of these other functions, and then I end up with those same values. I'm just evaluating the function at those spots. So now we're ready to graph this. Now that I have all my points in place, I'm going to be mindful of this hole. So whenever I graph around this hole, I'm going to go through the dots, and then approach that hole, pick up my pin, and go to the other side, and then move on. All right, so let's graph this. So I'm going to start at positive infinity, just because it's what works for my hand right now. We're close to the asymptote, slowly creeping off of it, swoop through the dots, and then go up the other asymptote, arrows on it. And then the same thing for our for this other side. We'll be starting this negative infinity, coming along this asymptote, gradually moving off of it, go pass through our hole, but skip over it, through the dots we've graphed, and then right along the other asymptote. All right, so one note, it's okay for your pencil to touch these asymptotes. If you want to find out how close they are, I could plug in, that's 4, 5, 6, 7, 8, 9. I could plug in a 9 and see where it is. But eventually, it's these your functions are going to get so close to these asymptotes that based upon the thickness of your pencil and the size of your graph, you're not going to be able to distinguish. Now, if you had the ability to like infinitely zoom in on those spots, then you'd eventually see that they don't touch. But there reaches a physical limitation where it's gonna look like that they touch. Now, the reason why I say that's okay is because some students, when graphing this, like let's say this hole right here, they want to get down to that hole, and then they just stay like parallel to the asymptote, and that is definitely incorrect. It needs to gradually be getting closer and closer and closer to the asymptote, and it might eventually touch. All right, so make sure that you understand the relationship between these asymptotes, and if you need to add more dots, add more dots. Let's take a look at the next example. All right, so again, we did this last time. This one, nothing reduced. So I did factor the denominator, but nothing reduced, so that means we have no holes. And this one is, I really like this example because it's quite interesting how it turns out. So I already have my x and y intercept graphed because they were both 0, 0. And you can plug your x values that we're going to pick into either of these forms. I'm going to go into the right one just because it looks a little bit faster and easier to be able to solve. I'd rather plug in a number, subtract 3, square it, and then multiply by 3, instead of plugging in a number, squaring it, and then having to deal with all of this math. Just looks a little bit faster for just me doing it by hand, plugging it into this one. So I'm going to pick this one, but it doesn't matter. All right, so let's take a look. All right, so I picked G of 1. Actually, let me back up just 1 second. Let me go through talk about my strategic points I'm picking. So 1, it's typically easier to pick points that are around 0 instead of picking numbers that are way far away, just because they typically are going to have easier math. But like I said, based upon my directions earlier, I need at least 2 dots on this side and 2 dots on this side over here. So 2 dots, sorry, let me clarify. Here's my vertical asymptote. To the left of that vertical asymptote, I need at least 2. And from this vertical asymptote to the right, I need at least 2. So anywhere on either of those sides. But, like I said, sometimes you're going to need more than just those 2 to be able to understand what's happening. So, and I'm okay with you including any x and y intercept points along with those at least 2 or at least 3s. So I'm going to do number 1 first. Evaluate what happens when I plug in a 1 first. What's also a good thing to know is I need to know what's happening to this function as I get closer to the vertical asymptote, because that's when the shape and the interesting things of this function sometimes tend to happening. So I need to make sure to pick numbers close to the vertical asymptote as much as possible, and then also pick something further along the end so we know what's happening. So I pick 1, and so when I pick 1, I evaluate it. I get 1 minus 3. Which is a negative 2, squared is 4. So I did subtraction and squaring in one step. And so this ends up being 4 over 12, which is 1/3. So that means that I can graph at 1, I can go up to 1/3. All right. Let's do my next one. So g of 2, I plug in a 2, subtract the 3, you get a 1, a negative 1, square, you get a positive 1, and we simplify and we end up with 16 thirds, which is 5 and 3 repeating. So I come over here, and I look at 2. When I go over to 2, I'm going to go up to 5.3. Whoa. So this is telling me that this is going to be doing this, which leads me to pause for 1 sec to go back and go, okay, did I do everything right? My function is 4x squared over 3 times x minus 3 squared. And I look at this, and I double check all my math, and yep, this is correct, right? So remember, horizontal asymptotes are guides. Around the center of this graph, around the origin and around the intersection with asymptotes and stuff, the vertical horizontal asymptotes, your function may cross horizontal asymptotes. You will never cross a vertical asymptote, but they may cross a horizontal asymptote. We talked about that last time because we saw an example of where you had an x-intercept on a horizontal asymptote of y equals 0. So when I'm at 2, I'm up at 5 and a third. So right there. So that's interesting. So we know that this function is touching my origin and then crossing up like that. That's interesting. All right, so I'm kind of curious what's happening to the left. So I know I already have 3 points, but clearly this is one of those cases where I need to do more than 2. And I'm already at 3. So let's see what else. So we have g of negative 1. So when I plug in g of negative 1, I'm at just a 12th. So over here, I can go left 1, up barely any at a 12th. That's interesting. Which also makes me realize what's happening, that this function is not crossing through the origin. It is touching and turning at the origin. I think I have one more point for this, a few more points here, so let me go ahead and do that, and then I can talk about this a little bit clearer. So g of negative 5, there we go, g of negative 5 is about a little over a half. So if I go over to negative 5, I'm up at about a half. Okay, so we know that this function, like I said, these asymptotes, these specifically the horizontal and vertical ones, but I'm talking about the horizontal one right now, they are guides. So as I go towards negative infinity, I knew that I would be having to get closer and closer to y equaling 4 thirds. So I knew that, this couldn't just go down that way. And it's also interesting that it didn't just cross through and go down, that it did go up. Now, why is that mathematically? Well, remember, how do we find our x-intercept? Well, for our x-intercepts, we set our function, we set the numerator to be equal to 0. So when I set the 4x squared to be equal to 0, notice that's basically like finding roots of a polynomial. And if I asked you to graph 4x squared, you would notice that it would have x-intercept of 0, and it would have a multiplicity of 2, right? It has an even multiplicity. And when it has an even multiplicity, that means that it touches and turns on the x-axis. So that's what's happening here. This function is going to come from negative infinity, but being at about 4 thirds, and then gradually coming down, crossing through, touching at the origin 0, 0, and then turning, and then sharply turning up and going up here, that asymptote. All right, so let me graph that part of this function. So it comes along this asymptote about 4 thirds, gradually coming off of it, going through that point, through that 12th, touching at the origin, and then turning quickly but smoothly, and then going up, writing up the asymptote on the other side, arrows because it keeps going. All right, so that's quite interesting for that rational function. So now let's see what's happening on the other side. All right, on the other side, I put in g of 4, and I get 21.3. So when I plug in 4, well, when I plug in 4 here, it's going to go all the way up to 21.3. This right here is at 10, so double that. So I know that it's going to be coming from this way. But it also gives me permission to not be right on that asymptote, but it's going to be a little bit further off. All right, it's going to just, I'll open up our next two at the same time. So G of 5 is going to be at 8 1/3, and G of 10 is going to be about a little over 2.5, 2.7. So G of 5 is going to be at 8 1/3. So here's 5, and then up there's 5, 6, 7, 8 1/3. So it's going to be about there. And then over at 10, it's at about 2.7. So over 10, 1, 2.7. So it's going to be about right there. So this one, coming from 4 being up at about 20. So coming down this way, curving and swooping through here and moving on. So this is one of those cases where from this view of the graph, it's not getting quite as close to the horizontal or vertical asymptotes. But if I was to zoom out, then definitely you would see that they would be approaching and getting closer and closer and closer to that. So this is that rational function. Definitely does not have that shape of just our traditional like pinwheel looking 1 over x, but this is a rational function. All right, let's do another one. All right, so we had our these two polynomials. They were factorable, and when it factored it, we completely basically lost our numerator and just left with a reduced 1. So the x over 4 is reduced to 1, x plus 3 is reduced to 1, and we're left with just 1 over x minus 1. Now when you have this, and it's just basically a graphical transformation, we can just go left 1. That's wrong. We can just go right 1. There we go. So let's go to the right one, and we could just graph those points. So from here, I could just graph, go half 2, 1, 1, 2, half, and graph those dots, -1, -1, -half, -2, and -2, -half. So you can just graph my parent function dots and be done with it. And that's what I have over here. So let me just uncover these. There's just that note that is just shifted to the right one. So we can use those dots. And here I've plugged in the dots and I've gotten those values. So let's plug in do those dots and swoop the graph. So half 2, 1, 1, 2, half. And I'm counting as if this the intersection of the asymptotes is 0, 0. That's how I like to graph my rational functions. Then -half, -2, -1, -1, which is already graphed, and -2, -half. All right, and then let's swoop our dots. So come along the asymptote, gradually coming off of it, swooping through your dots, and then riding up the other asymptote. Arrows, and then the other one. So here, coming along this asymptote, gradually coming off of it, coming up to that hole, hopping over it, going to the other side of the hole, hopping through that hole, and then passing through my points that I already have graphed, and then up through the other ones. There we go. Oh, and an arrow. Alrighty. So there's this rational function, all graphed. All right, let's take a look at our last example. So we have k of x is -x over x squared minus 9. And when we worked this last time, we went ahead and factored it, and we noticed that nothing reduces. So because nothing reduces, we have no holes, but we do have two vertical asymptotes, one at x equals -3, and one here at x equals 3. When we also got our x and y intercept to also be 0, 0. In a minute, whenever I plug in my values, I believe that I plug them into this left one, just because it's just going to make my, that mental math, that substitution a little bit quicker and easier, substituting this left one instead of doing the right one, but it doesn't matter which one you do. Now, before we start plugging in numbers, if you just take a look at our graphed asymptotes and our intercept, you notice there's two different kinds of symmetry going on here, which leads itself to potentially be either an odd or an even function. Now, in a second, I'll talk about why it in fact is odd using the function itself, but just looking at this setup, this keys me in that I should check this, because notice if I look at my vertical asymptotes, one at +3, the other at -3, they are they have nice symmetry because they're on either side equally. I also have this horizontal asymptote going on the x-axis, and then my x and y intercept are exactly in the same spot at 0, 0. Now, what this means is that if it was even, then that means, if you recall, that it's symmetrical around the y-axis. So these asymptotes could easily swap around if it's symmetrical about the y-axis, and then same thing with this ordered pair at 0, 0, and this, if it reflects over the y-axis, it's the same thing. If it's odd, like it's going to end up being, what it means is, if I was to pick, basically this entire thing is symmetrical around the origin. Pick any spot on this graph and spin it 180 degrees around the origin, and it will end up in a similar location on the other side, and the picture will not have changed. So just the setup is potential to be odd, and let's check and see if that's the case. So we check and see if it's an odd or even function by plugging in a negative x into the function and evaluating. So f of negative x is, well, negative x, and negative times a negative x is a positive x, and then a negative x squared is a positive x squared. So if we compare this to our original function, I end up with an x over x squared minus 9, but my original function is just a negative version of that, a negative times x over x squared minus 9. So this is literally just f of x that's been negated. So whenever this is true, it's an odd function. Recall for it to be an even function if you plugged it in f of x, and it would end up as being just the same thing, meaning nothing changes when you plug in that negative, then it would be even. But that's not the case here. All right. Now, actually, sorry, extra side note, extra 2 cents. If for some reason this, instead of being this negative here, if this was a squared, or even, I could even technically, even if that negative is still there, if this was a squared on top, then this would have ended up being an even function. All right, so let's graph this. Let's plug in our points. So first up, a big chunk of them I can undo at once, or unveil at once. If I plug in f of 1, f of 2, and f of 5 halves. Remember, I only need 3 between these two bars, but it got kind of interesting, because when I plug in a 1, I get a point at positive 1.25. So if I plug in a 1, it's at positive 1/8, so barely up any. Plug in a 2, I'm at 0.4, so not even quite a half. When I plug in 2 and a half, 5 halves, 2.5, I end up at 10/11ths, so just about 1. So that's kind of interesting that it's gone so far over and still barely gone up any. But if I keep picking points closer and closer and closer to the vertical asymptote, it's going to be getting closer and closer and closer, and just do this. This wants to get as close to those vertical asymptotes as quickly as possible. All right, I want to do the other side. Because it's an odd function, I actually don't have to do all the math all that much, because I know that this 1, 1.25, has odd symmetry. It's going to become a negative. It's going to be at -1, negative 0.125. Or you can go ahead and plug them in. But like I said, because it's symmetrical about the origin, we're going to have these points. So when I plug in a -1, I'm at that -1/8, or negative 0.125. When I plug in a -2, I'm at negative 0.4. And when I plug in negative 2.5, or negative 2.5, or negative 5 halves, ooh, I just realized that's the wrong number. This should be a negative 5 halves. Yikes. Wrong thickness. Negative 5 halves. There we go. Negative 5 halves, I'm at negative 10/11ths. So this is, you can tell it has like a familiar odd shape to it. Kind of feels like a cubic. Very much not so, but like if I've stretched it and then compressed it into these asymptotes, sort of kind of has that feel. So it's going to be, we're basically on top of this asymptote, and then at some point coming off through them, and then swooping through these dots, and then going up closer, 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 and basically on top of the asymptote at this point. All right, so that's the center part of this function. All right, let's do the next chunk. So at least 2 from vertical asymptote to infinity. So here's 4 and 5. So 4 is at a negative 4/7, so that's a little over a negative half. And then 5 is at a negative 5/16, and that's around a third, around a negative third. So what was it, 4 and 5? So if I'm at 4, we're at negative a little over a half. And if I'm at 5, it's about a negative third. So we see that kind of which side that it's going, that it's just from these 2 points, I see that it's getting closer here. And then also I see that it's heading down. It's often a good idea to check. You can maybe check a 10 to make sure that it stays under. It doesn't, actually no, take that back, sorry. I know that because I only have the one x-intercept, it does not cross up and back over. So it doesn't do anything weird like that. So I know it's not crossing the x-axis any more than that. And then so it's headed down this way. So I know it's not passing my horizontal asymptote anymore. All right, so let's swoop these dots. So coming up along this vertical asymptote, gradually coming off, swooping through the dots, and then closer and closer, closer to the asymptote on the other side. Now, because of the odd nature of this graph, I know that it's going to be here on the other side. So we get this. And then so we have, it is at negative 4, I'm at positive 4/7, and negative 5, I'm at a positive 5/16. So negative 4, I'm at about a half, a little over half. Negative 5, at about a third. And then let's graph these. So I'm going to come from this asymptote, basically right on top of it. And then at some point swooping off of it. And there we go. All right, one just last little thing I want to point out. So notice on this function, my in terms of the vertical asymptote and where they're going in opposite directions. They're not on the same side of the vertical asymptote. But then if I look back at this g of x, notice that if I was to keep going to infinity, these would be basically going like side by side with each other, never touching, but I was getting closer. The reason why this happens is just like we have multiplicity with our x-intercepts, where this touches and turns, the same thing happens with our vertical asymptotes. Because I have 2 vertical asymptotes on the same location, basically, what happens is we basically have like a multiplicity of this factor in the denominator. When that happens, then we end up, when it's even, the 2 parts of the rational function are actually going to be side by side. They're going to be going together instead of in opposite directions. So it kind of has that multiplicity feel. That's something that I'm going to have you like observe and write down. But if you notice on all these others that we have, that it has this, they go in opposite directions because there's just one. If you just simply graph 1 over x squared, that function is just this, where we have it going like this and going like this, arrows in both directions. So it has that idea of that multiplicity of that vertical asymptote of x equals 0. All right, so I hope all this helped you put the pieces together and better understand what we did in the last video and compared to this video, then putting all those dots together. It's a little bit just of tedious work. So pick at least 2 dots from their asymptotes to the infinities, and then at least 3 dots between your vertical asymptotes. If you need more, do more by any means, and just be able to check those. Again, if you remember, you can feel free to check this using graphical software like desmos.com, DESMOS. I'll put a link in the description below, so you can plug that into a graphing calculator. It's what I used last time when I introduced this, so you can play around with this just to make sure that what you graphed ends up being what it actually is, and be able to help and check your work. All right, hope this helps, and we'll see you in the next video.